We are on topic 10, and what we're going to do is show how to use Apply.Desmos to exponents. So we start off with some very simple examples here, and the first thing we have to do is that we can't use x or y because it won't accept exponents with those kinds of high powers, so x to the fifth. So we're going to use letters a and b. And so here we just settled on a equal to 3 with a slider. You can choose any value of a that you want. Put in a equals something, and then the slider will come up. Probably better to use a number between 0 and 10. And you can see a to the fifth, which is really 3 to the fifth, is 243. We get the same answer by multiplying a by itself 5 times. 1, 2, 3, 4, 5. So we're showing that these two expressions are equivalent. In addition, if you multiply a cubed by a2 by the product rule, you add the exponents 3 and 2, you get a to the fifth. So you should get 243 because 3 to the power of 5 is 243. Now, to differentiate the product rule and the power rule, the power rule is when we've got a cubed and we square it, we multiply these two together. We don't add the powers. So 3 times 2 is a to the 6th, and 3 to the 6th is 729, and you can see here I've done the same thing. So these two are the same. So what are we trying to illustrate here is that you can differentiate very easily between the product rule and the power rule just by doing simple calculations in decimals. Not everybody will find this useful, but we'll see later on. Maybe you'll see that the applications that we give are more interesting. So here again, we multiplied a to the minus 3 times minus 2. Minus 3 times minus 2 by the power rule is plus 6. 3 to the 6 is 729, which is the same as what we got over here. We multiply 3 times 2, we get 6. 3 to the 6 is also 729. Now, here we've broken this problem down into a number of steps, a to the minus 5 over a to the minus 2. And what I did, I brought this denominator term up, so I get minus, because I bring it from the denominator to the numerator, and it is minus 2 already, so minus minus 2. And this becomes plus 2. In other words, I've changed this to this, and the number here doesn't change, nor does it change from there. And minus 5 plus 2 is minus 3, and this is the same as this. And because we're supposed to leave exponents positively, the exponent's positive, I brought this from the numerator to the denominator, changed the minus 3 to the plus 3. 1 over a cubed is still the same number. So I can sort of break down a problem into small steps and show that the values are the same. Now, I have to tell you that probably mathematicians wouldn't be very impressed with this way of doing things, but I think it's an interesting way how you can use decimals. Now we get to something a little more complicated. What we're going to do is have a and b. So we're going to say, we already know that, we look up here, a is 3, b is 4, and we're going to have m and n also defined. Now the numbers that I put in here are, doesn't really matter. I'm choosing positive ones. The key thing is when you go over, for example, to this one, let's take this one an example. Let's just go back for a minute. If we change this value here, these numbers should always be the same. These three should be the same. So that's one of the key tests that you have to do. So here I've shown a times b to the nth power, which really means 3 times 4 is 12. 12 to the power 5 is 248,832. And over here, I've removed the bracket here. There's an implied 1 here. A to the 1, B to the 1. 1 times n gives me n. B to the 1 times n gives me b to the n. So this is the same as this, and I get the same numerical answer. If I do this, I've got a, b, brackets to the nth power, the whole thing, bracket to the nth power. It's the same as saying a to the m times n, right here, b to the m times n here, and I get exactly the same answer. Now, if I take a to the minus m and b to the minus n, I bring this to the denominator, it becomes a to the m. I bring the b to the minus n to the numerator, it becomes b to the n. So this and this is the same answer. And I can go back, change the values of m and n on the slider, and make sure that these two numbers stay the same. Now, the reason I do this is because we're always supposed to report the answers with positive exponents. Here, I've got a over b to the minus n, which is really the same as b over a to the plus n. So I put the numerator up to the, the denominator up to the numerator down to the denominator. In other words, I flip this and I get this, and these two are the same. So let's go to a problem on page 50. We have a and b right here, and we have this to the minus 4th power. We did this problem, and the answer is a to the 6, b to the 4. So the first thing I do is put in the sliders for a and b, or just put a into a number now. It doesn't have to be 1.17. It can be any number that you want. Usually I choose positive numbers, and as I do the problem, I always make sure that the value of a and b in each the resultant value in the boxes below a and b are always the same in this problem. So we start off, we enter the problem in box 3 here. And now we multiply minus 2 times minus 4 gives us plus 8. 3 times minus 4 gives us minus 12. Minus 2 times minus 3 gives us a to the 6. B squared times minus 2 gives us b to the minus 4. And there's an implied a to the 1 and b to the 1, and 1 times minus 4 gives me minus 4, and the b term gives me minus 4. And you can see that in going from here to here, I've done everything right. If I had not, these two, the numerical value of these two would not be the same. Doesn't matter what they are, they have to be the same, and they have to be the same when the sliders for a and b change. So now what I'm going to do is group the a term. So I've got a to the 8th here. I bring this one up from the denominator to the numerator, it's minus 6. And bring the minus 4 from the denominator to the numerator, it's plus 4. So I've grouped all the a terms together. Now I'm going to group the b terms. Minus 12. Bring this up, it's going to be plus 4. Bring this up, it's going to be plus 4. So I get this. And you can see that this is obviously equivalent to that because the number is the same. Now what I've done here in going from box 5 to box 6, I've left this term exactly the same, and I brought this down to the denominator and changed each of the signs. So the minus 12 becomes plus 12, the minus 4, the plus 4 becomes minus 4, and this plus 4 becomes minus 4, and this becomes a to the 6th. If we add these terms, 8 minus 6 plus 4 is 6, and 12 minus 4 is 4. Now, why did I bring this down? Because I want to make the exponents of b positive, and I can see the minus 12 when it comes down is going to be plus 12, and it doesn't really matter what these are, because when I add them they become minus 8, and so the term will still be positive. Now you could have worked this one out and said that this was a to the 6th, and you could have worked this one out and said it was b to the minus 8 as the next step, and then put this as the final step. So we get the final step, 8 minus 6 plus 4 gives me 6. 12 minus 8 gives me 4. This number doesn't change, so we know we've done the problem right. Now we go to page 50. We're going to do this one, and instead of using x and y, Desmos doesn't like x with and y with very high exponents, and it'll try to graph them, and it won't work. So we're going to use A for x and B for y and just replace it. So here's the original problem, minus 2AB minus the minus 3 to the minus 3 over AB minus 1 to the minus 1. So I've replaced the x with A and the B with y. Doesn't matter what these initial values are. Okay? Now, I do minus 2 to the minus 3 is this term right here. A to the power 1 times minus 3 is minus 3. This minus 3 multiplied by that minus 3 gives me plus 9. And A here is a to the minus 1. Minus 1 times minus 1 is B1. So now what I try and do is, because this is minus 2 to the minus 3, I'm going to bring this down. It'll still be minus 2, but to the plus 3, because this minus 3 exponent changes to plus 3 down here. So I've just brought this from the numerator to the denominator, so the exponent is positive. This doesn't really matter. Okay? So here I have B9. Here I have B1. I group the B's, 9 minus 1. I group the A's over here. I'm going to bring this down from the numerator to the denominator, plus 3 minus 1, because I want the exponents to be positive. 9 minus 1 gives me 8. Minus 2 times minus 2 times minus 2 gives me minus 8. I put the 8 here and the minus sign here. Right? Doesn't matter. I could leave it here, but put it in front here, minus 8. And 3 minus 1 is 2. Notice, doing this in steps, these values don't change. I change the values, I look at this, and I go back and I change the values of, right here. Change the values of A and B. I use in the live version, and I make sure that these numbers here in the bottom of the box all stay the same. So I've broken this problem down into small steps, and this way I have made it easier for me to verify my problem, or even to diagnose where the errors are. Because, for example, if I made an error going from here to here, I could then try to figure out which of the individual steps was important. If I got that far and I made an error in this box, then I would try to rework this one, see where I made my error in some sign or something like that. So I think you can see that Desmos becomes a useful tool in determining or verifying answers using exponents.